The next talk is by Samir Murthy, and the title is Gravitational Index of the Heterotic String. Please.
Okay, thank you very much. Thank you for the invitation. And my special thanks to the organizers for helping me and bearing with all my visa troubles, both last year and this year. Well, last year and this year. Unfortunately, it didn't work out last year, but I'm happy to be here this year. So my title is this, Gravitational Index of the Heterotic String. And as we shall see, in content, there is a significant overlap with Ashok's talk this morning. But in fact, we discussed this, and we both felt that it's not necessarily a bad thing to repeat a discussion on something interesting, and hopefully it's a slightly different point of view. Okay, please feel free to interrupt with questions and comments. That helps me a lot. So let's begin with the main question. Consider a supersymmetric compactification of heterotic string theory to some number of dimensions where the compactification manifold contains at least one circle. Okay? So in order to be concrete, and we take the simplest example, today we'll just consider heterotic string theory compactified to 4 dimensions on a 6 torus. Okay? This theory has 16 supercharges, and in this theory, consider a fundamental macroscopic heterotic string which wraps this circle W times, winds around this, and carries n units of momentum. Okay. Now, as we all know, the supersymmetries of the heterotic string arises from the right movers. So if we set the right moving oscillators to the ground state, this configuration is supersymmetric. It preserves 8 of the 16 supercharges of the theory. And its mass is determined by the right moving momentum Kr. But you can excite the left moving oscillators to arbitrarily high energies. And so you get this infinite tower of BPS states, okay, all of which have the same mass. And it's fairly easy to estimate what the degeneracy of states of this tower is. Ashok even gave a sketched derivation. And the answer is that d of the asymptotic degeneracy of states goes as exponential of 4 pi times square root of nw. Okay. Now, the main question is the following. This doesn't work. It works. So this was a free. Sorry. Well, I already flipped this. But then this will go away from me. It's over here. Yeah. Okay, I'll try this. Okay, let's try this. Now it's worse. I'll just move this. Yeah. Okay, so this was a sort of a description of the free or weakly coupled string, and the main question is what's the description of this ensemble of states, this tower of states, at strong coupling? Okay. Now, this question was asked by Ashok in 1995, and I remind you that a year later, exactly the same type of question asked for the 3-charge system, the D1D5P system, led to the famous breakthrough of Strohm-Wien-Jenwaffe. Okay? However, this original question still remains unsettled. Okay, and I'll discuss why that's the case. But first, let me just explain what I mean by this question a little more. I'm just going to, yeah. So I'll say what it's not firstly, especially given this audience. So what I want is I'm looking for saddle points. Okay, so I'm thinking of the path integral, and there's this ensemble of states, a large ensemble of states. So in the Euclidean path integral, there should be a saddle point that describes that. Okay. So in the gravitational theory, when G Newton is small, saddle point means that it's a solution of the equations of general relativity coupled to the matter fields. Okay, so I say this just to distinguish it from the question of how to describe each individual microstate. Okay, in fact, this 2-chart system, we know very well what the description of the individual microstate is. Okay, starting from this original paper which started the fuzzball program. So that's not what I want to discuss. Okay, so saddle point. Now you might say, well, that's actually, it's funny that you're asking this question because don't you have the black hole already? Indeed, you have some exponential degeneracy of states. The first guess that the saddle point is the black hole, and these states are supersymmetric, so the black holes would be supersymmetric, and in all other examples that we know, supersymmetric black holes are extremal, so you should look for two-charge extremal black holes. This was done soon after this tower was discovered. It's a very easy calculation of two charges, so you have two harmonic functions, you write an ansatz, and you solve it, and you find, I think I'm going to give up on this, find that this solution is singular in the sense that the horizon is on top of the singularity. Okay. Now, the next step is to say that this singularity is really an artifact of the two-derivative approximation to string theory, and if you include higher derivative corrections, alpha prime corrections, then there's a chance that a horizon develop and shields the singularity, and that horizon will be of string scale. This is the stretched horizon that we heard about earlier. Now this is a difficult problem because you're talking about higher derivative theories of gravity, and in order to make progress, one makes assumptions about the near horizon geometry of the black hole. Okay, you say that the near horizon, like any other extremal black hole, should have symmetry enhancement. So there's an ADS2 times S2 times a T6, and correspondingly the supersymmetries should be enhanced to 16 supercharges. Okay. Now with this assumption, all the tensor structures are fixed, so it's even with the four derivative theory. You can make progress in calculations. Okay, and that was done here. But what I want to say, I want to point out a certain problem with this, that in fact, there is no solution in 10-dimensional supergravity that is known which preserves all these symmetries. So I want an SL2 and an let's just say geometry which has an ADS2 times S2 times T6 with 16 supercharges. Okay. So remember that whenever I have an ADS2 times S2, it admits at most 8 killing spinners. So one doesn't really know this kind of a solution. You might say that this is something about not finding solutions, but in fact, you can abstract this idea. The symmetries of this would be SL2 times SU2 times U1 to the 6th, and you'll have 16 fermionic generators, and you look at the list of supergroups, and there is no such supergroup with exactly that, those symmetries.
What was the original motivation of this assumption?
Sorry, of which assumption?
The assumption of ADS2 times S2 times T6.
Well, so as I said, firstly, this problem is very difficult to solve otherwise, and secondly, if you have an extremal black hole, then typically you have such a symmetry enhancement. Okay. Sorry, Nick.
Why 16 supercharges?
Well, so there's remember that when you have ADS2, then if you have some supercharge, there's also a conformal supercharge. So the supersymmetry should also double.
You started with ADS.
So I started with heterotic strings. I have 16 supercharges. The black hole, the fundamental string solution breaks half the supersymmetry, so I have 8. And so I should get 16 again. Email. Here.
Does the extremal limit of the black hole solution carrying these charges have a near horizon ADS2 region?
Well, so that's exactly what I'm saying. We don't know how to solve, so maybe I didn't spell it out. The four derivative theories, as you,
so the idea is you need to first go to the four derivative theory, then ask, and then are you assuming that has a solution with this symmetry?
Exactly, that's exactly what I tried to say. The two derivative solution is singular. So you have to go to four derivatives, and the idea of Ashok is that there is a solution.
Right.
That's difficult to calculate. We don't know how to make progress. So you assume that there's a near horizon geometry which looks like this, and then you can do calculus. Okay, but I want to point out that there is a Jose. I want to point out that there is a gap here.
If you relax, if you relax the number of supercharges, you find solution.
You have a solution with 8 supersymmetries.
And why you don't take into account?
Well, because we know that ADS2 also always enhances supersymmetries, right? For every supersymmetry, the conformal supersymmetry.
Because four charged black holes always have this type of.
Sure. So that's why. That's why this problem that I'm pointing out doesn't apply to big black holes, right? So big black holes, for instance, would preserve 4 of the original 16, and they'll be enhanced, and I'll get 8. Okay. This is not a theorem. Ashok has a comment. This is not a theorem. I'm just saying that there's something funny about this.
Yeah. So I was just saying, if we just take the gravity Lagrangian with this additional 4 derivative term added, then there is a near horizon solution of this kind.
Yes.
Right.
Yes.
So the question is what to make.
So this is a question which I want to discuss this.
So the solution does exist.
Yeah, of course. Yeah.
The near horizon
the
geometry.
bosonic exactly.
Yeah.
Okay. Now this I'll call a kinematic problem. It has to do with symmetries. There's also a dynamical problem, which is that there is another solution due to Horowitz and Polchinski, which is often called a self-gravitating string gas. What it is this is a Euclidean theory. I mean, the time circle in the Euclidean theory becomes sort of the right size. The lowest mode of the heterotic string, which would be tachyonic, becomes nearly massless, and so it can condense. And with that new degree of freedom, they wrote down a new solution. And in this paper, they showed that there are such solutions, Horowitz-Polchinski solutions, type solutions, carrying all the charges of the fundamental heterotic string. Okay? And it was argued in this paper, Chen, Maldacen, and Witten, that the near extremal states of this two-charge system are likely to transition there instead of the black hole. Okay? Now, I'm not sure that's completely familiar with this audience, so I'm just going to review this briefly. So this is from Chen, Maldacen, and Witten. So let's look at the left diagram. So this is the mass or the energy in units of the extremal energy. So I'm fixing charges as a function of temperature. Okay. So up here, the black hole solution is completely well defined. It's some non-supersymmetric. So this is the extremal black hole. So it's a non-extremal, non-supersymmetric black hole with a good horizon. You can study its thermodynamics. And then you can ask, what happens to the thermodynamics when you reduce the mass? Okay. Now, you might naively expect that as the mass approaches the extremal mass, the temperature should go to 0. But that's not what happens to this. That's what usually happens in extremal black holes, but that's not what happens to this black hole. The temperature actually starts to increase. Okay? Now, of course, close to the extremal limit, you don't trust this solution for reasons that we just discussed. It becomes highly curved. But if you extrapolate it, you find that there is some maximum temperature, which I'll call 1. Okay. Now let's look at this graph. Here I've plotted the entropy in units of the extremal entropy as a function of the temperature. And same thing. So you can study the thermodynamics of the black hole, and then close to this it breaks down. But if I extrapolate it, instead of going to 1, it goes to 0. Okay. Well, it's already the fact that temperature is increasing at near the extremal limit should worry you. Okay, so I'm just saying, I'm pointing out that there's something funny about this, the thermodynamics close to extremality. Okay, and here it's as if there is no entropy there. You can think of this as two funny properties. This orange curve is the Horowitz-Polchinski type solution, which was studied here. Again, it has its regime of validities. So the dotted means that I'm extrapolating. But you see that it fits very nicely. So the idea is that, so here, as you go towards extremality, indeed it goes towards 0 temperature, and it goes towards the right entropy. So the idea is that the thermodynamics of the near extremal states would go this way and then switch and go this way. Okay, so this was the argument of Chen, Maldacen, and Witten. This is not the approach I want to take. I don't want to think of sort of going to the near extremal states as a limit. I want to directly consider the supersymmetric states. Okay, and I want to ask, so there is an exponential growth already in the supersymmetric states, and I want to ask, what's the gravitational saddle corresponding to these states? Okay. Now, in order to answer this question, I need some observable which is defined in the full theory, but somehow only picks out the supersymmetric states. Okay. Now, such a gadget has been with us for years. That's the supersymmetric index. That's exactly what it was designed for. Okay. So that's where I'm going to move to. But any other questions until now? Emil?
So, following on the previous slide, so is there a version of the index calculation for
the IPhT-TV? That's a fantastic question. Another question for discussion. Yoav might have more to say than me. He says no, but
okay.
What I said is still true. You still have more to say than me. Okay, but this is something which is a great discussion. Okay, so let's so everybody knows what a supersymmetric index is, but just to what Roberto said, just to make sure that everybody went to different kindergartens, so just to put us all on the same page. So the context is I have some supersymmetric system with a complex supercharged Q with this superalgebra. QQ dagger is the Hamiltonian, and in this I'm going to write something like a thermal partition function, except that I'll put -1 to the f. This is the Witten index. Now, so typically the quantum theory will look like this. There's the bosonic and fermionic states, and if you study the representation theory, you'll see that everything with energy greater than 0 comes in boson-fermion pairs. Now, one point is that in order for this index to be defined, I need a non-zero beta, because this is some infinite tower of state. So for the convergence of the trace, I need a non-zero beta. This is how Witten defined it. But because of the pairing and the -1 to the f, this z is independent of beta. Okay, and it's equal. It reduces to the number of bosons minus the number of fermions, the unpaired states at 0 energy. Okay, the same argument also tells us that this index is actually invariant under any deformation of the Hamiltonian, as long as this deformation is supersymmetric. So because any supersymmetric deformation will always change the spectrum in pairs, so this argument stays exactly as it is. Now, what we want to do is to use this and so calculate this in the microscopic regime, and then extend this calculation to the gravitational regime.
I thought that there is a subtlety in the index that you want a finite volume in order for this.
Yeah, so there are many assumptions which I didn't spell out. Part of it has been encoded in this picture. So one of the assumptions is that there's a mass gap, energy gap, and so there's no continuum of states. Another assumption in the theorem is that what Witten calls there are no states coming in from infinity. Okay, there are all these things which have for the indices that we're going to calculate. They obey all these assumptions, so there's no issue.
My comment is Chenmal, the son of Witten, compactified the target space in order to talk about the.
Yes.
Do you also need to compactify the
You'll see that in the indices that we calculate, it's sort of the index is already well defined. Okay, so there's some effective compact target space if you want. Okay. Now, of course, these are 0 energy states. If you want to discuss black holes, you want states with mass. So you have to sort of soup this up a little bit. You have to go to some sort of the next simplest situation. And you can do this in many different contexts. Today what I'll discuss, this is probably the simplest context, is 4-dimensional n equal to 2 supergravity. This has black hole solutions. And again, there's one complex supercharge. I said QQ dagger is now not energy, but energy minus the BPS mass. Again, I'm fixing the charges. So the BPS mass is a function of the charges, and that's the superalgebra. And the index, again, I can write some trace -1 to the f times e to the minus beta e. Now, just a technical comment is that it's not exactly that, because if you compute this in this theory, you'll get 0 because of some extra fermion 0 modes. We had a discussion about this morning, so I don't want to discuss this much. You can absorb those fermion 0 modes, and then that'll just give some constant up front, and the answer just reduces to an index of this sort. Another comment to make there is that in other contexts, like in asymptotically IAS spaces where you have a super conformal index, you actually don't even have those 0 modes, okay, because the representation theory is different. Okay, so essentially always we are studying indices of this type, so I'll go ahead with this. Now let's unpack this. So E is QQ bar plus MBPS, and now you see that this part of the index, just this much, is exactly like the Witten index, and this is just some fixed function, beta times mbps. Okay, so I can rewrite the whole thing as some index called d micro times e to the minus beta mbps. So the whole thing is completely fixed by the charges. Okay. And now I want to ask, before that, for example, if I calculate this for this two-charge system that we discussed in the first page, you'll get exactly e to the 4 pi square root of n double. Okay. Now, having said this, from now I'll sort of broaden the context. I'll get out of this two-charge system, and the discussion in the next many pages will apply to arbitrary supersymmetric black holes. Okay, many of the points that I'll make applies to that, and then at the end we'll come back to this two-charge system, right? Now, the main question is, so this is the value of the index. I can calculate this in some examples, and the question is, what's the meaning in gravity? Okay, so when I crank up, so this is some weak coupling calculation, then I make the coupling strong, and what is the meaning? Now, in gravity, there is no trace. We don't know of a Hilbert space, at least not for the most general black hole. And so that's not the right way to do it, but you do have a path integral interpretation. So already in the weakly coupled regime, you can write this as a path integral by the usual rules of, this is just quantum field theory. And then you can sort of mimic that in gravity. There's some gravitational path integral, which we don't have a good meaning, we can't give a good meaning to in the UV, but at a saddle point level, this is perfectly fine. Okay, this is exactly like we saw in the last talk. So here, this is some schematic. This is an integral over all the fields of supergravity, bosons and fermions, with the supergravity action, with the caveat, or rather with the condition, that there's a thermal circle, the time circle is periodic, with period beta, and all the fields, including the fermions, are periodic. Okay, that's what implements -1 to the f. Okay. Now, the question is, what are the saddle points? So that's the only thing I want to answer in today's talk. Okay, this is the gravitational index. This is the meaning of the gravitational index. What are its saddle points? Now, I should say that this is not just an academic question. In all situations in string theory microstate counting, what you really expect to agree between microscopics and microscoping is the index. Okay, anything else that happens needs more explanation. Sometimes it's an accident, sometimes extra symmetries. But the index is supposed to be protected. And in all the examples that we really know, that's actually what's happening, starting from Strom-Wien-Waffe. Historically, it's not been understood this way, but in hindsight, this is the right way to think about it. Now, given that this value in all these examples that we know of agrees with the black hole entropy, the first case might be that indeed the saddle point of this is the extremal supersymmetric black hole, okay, for arbitrary charge configurations. Okay. Now, this cannot be the case because in gravity we expect something like this. So you have some asymptotic thermal circle, time circle, and then some large spatial sphere. And then you want solutions with some finite action. Typically, a black hole solution looks like this. There's some cigar-like topology. There's a cap. Okay, it's a non-extremal solution which fills in this with obeying the equations of motion. Okay. And the extremal black holes have 0 temperature. They have beta goes to infinity, so they don't fit this. Okay. You can try to fit it artificially. You can say, I want to, so this gravitational path integral is the dual of the Witten index, as Witten defined it. Okay, you start with the finite beta, and you do periodic boundary conditions for fermions. Now, you can try to fit in an extremal black hole to this by saying that these are my boundary conditions, I'm just going to solve the extremal equations of motion. Okay, people have tried that, and then you get an inconsistency. You either get a singularity, or you can get around a singularity, find some solution, but that has 0 entropy. Okay? So that's the first problem. The second problem is that this cigar topology admits only one smooth spin structure, but that's anti-periodic at infinity. It's the opposite of what you would expect from supersymmetry. Okay? So there are these two problems. I should say that, so this is what I want to discuss today, but I should say that, of course, there's been a lot of progress, as all of us know, even in this subfield of explaining Euclidean the Euclidean entropy of black holes from this Euclidean functional integral approach. That's been extremely successful, but at the level of formalism, there's a bit of a gap, which is that there's some kind of mixture of Hilbert space and functional integral formalism. You start with some, let's say, asymptotic flat space, and to first approximation, you think of one black hole or multi-black holes as particles, and you treat the whole thing as some Hamiltonian Hilbert space approach. And then once you that's easy to quantize. Once you get rid of the things outside the horizon, you go close to the horizon of one black hole, the extremal black hole. There you have ADS2, and there you use the functional integral. So it's this sort of, you have to make your way around it, and it's been extremely successful, but I want to have some kind of uniform functional integral description starting from infinity. Okay? In ADS5 or ADS4, this takes even more, so it's even more pressing because of the ADS-CFT correspondence starting from infinity. Okay. Now, the resolution of this has been known for some years now, and the idea is as follows. So this is a paper with Alejandro Cabo Bizet, Davide Cassani, and Dario Martelli. It's in the context of supersymmetric black holes in ADS5. And the idea is that, so you solve the second problem first. So instead of -1 to the f, you exchange -1 to the f with a holonomy for any gauge field that carries, which couples to R charge. Okay? So R charge means that fermions and bosons are coupled differently by definition, and that's why you implement -1 to the f. And then the question is there a solution? Is there a gravitational solution? So what you've done is to exchange the fermionic problem for a bosonic problem. This is a bosonic potential. Solve the bosonic equations of supergravity, and the question is there a smooth solution of this type? Okay? And this is what we found in this paper. And the solution is complex, and this is generically the case. So either the metric or some charge or something becomes complex. We saw some discussion of this in the previous talk. The solution necessarily carries R charge, and that's because you've turned on a chemical potential for R charge, so the solution also, there's a condensation of charge. Okay, that's an important comment, but it may not be completely transparent. I'll make this more clear very soon. And the action, you can calculate the action of the supergravity theory, turns out to be independent of beta. That's the free energy of the theory that turns out to be independent of beta. Okay? And that's exactly, these are the properties, these two properties are, this last property is exactly what you would expect from a saddle point to the index. I should have said that it's a smooth solution. That's another thing you would expect. Infinity, when beta goes to infinity, then in this case, this actually goes back to the extremal solution. Then it just at last point you recover the reality. And the action is independent of beta, so you can define it as a limit, and limit is smooth because of this. Thanks. Okay. Then this logic was extended to many other, so this sort of free energy was then used by our group and other groups to sort of solve the problem of the ADS-CFT index, and one has to sort of recover the same index from the super-Yang-Mills theory and so on. Again, that's not today's talk, but that's where it was used for, and then it was extended to various ADS spaces, okay, with the same kind of motivation, and then in this nice paper also to flat space. Okay, so in this paper they treated pure supergravity in a asymptotically flat space. And here, this holonomy takes a particularly simple form. Okay, so I said R charge very generally here, and in fact there was a question in Ashok's talk this morning. So R charge so there's always one universal R charge, namely angular momentum, because of the spin statistics theorem. Fermions and bosons have half integer or integer angular momentum. But there could also be other gauge R charge in the theory. That depends on your theory. And typically in gauge supergravity, there are like multiple R charges. And there was a question as to which one should we pick. I forgot who asked which one we should pick. And the answer is you can pick any combination as long as it implements -1 to the f. Okay? Here, you don't have a choice. There's only angular momentum. It's ungauged supergravity. And so this potential is just the angular velocity. And so this holonomy condition just becomes beta times omega equals to pi I. Okay? And now from the Gibbons-Hawking perspective, it's clear why it's doing its job, because Gibbons-Hawking would say that given a temperature and angular velocity, the gravitational path integral calculates for you trace e to minus beta h minus beta omega j, and that's exactly by spin statistics, that's minus 1 to the f times e to the minus beta h. Okay? Question?
Yeah, I also asked this in KITP. What happens in 2D? In 2D, I would have expected that there is a well-defined index, but there is no plane of rotation, if it's just time and radial coordinate.
Yeah, so 2D has many other things which is not the same, like spin statistics also takes a funny form. But I haven't thought this through completely. I don't remember you asking me, but I believe the same. I believe an index can still be defined in. Yeah, I'm pretty sure the index can still be defined in 2 dimensions. Yeah, so there's. Yeah. You still have a notion of an R symmetry for the quantum mechanics. So that's why I like this way of writing it much better than, this spin statistics is an example of this. Even 0 plus 1 dimensional quantum mechanics allows for R symmetries. Okay, so let's move on. So what do I want to do today? Today I want to lift this whole discussion to string theory. Namely, I want to discuss the Strominger-Vafa type black holes. Okay, so the simplest situation is 4-dimensional, so 4 charged black holes, but I'll be talking about n equal to 2 supergravity coupled to supersymmetric matter. Okay, this is the situation in which you can embed these supersymmetric black holes in string theory by thinking of this as type 2 string theory on a Calabi-Yau manifold. Okay, and in this context, I want to present these non-supersymmetric rotating saddles. I wanted to say something here, which is that notice here this comment that the solution necessarily carries R charge. So the extremal black hole in 4 dimensions in asymptotically flat space does not rotate. Those of you who have done this, it's a fairly simple statement. But these solutions necessarily rotate. Here the R charge is rotation. Okay, so that's an example of this statement. Okay, we'll see this as we go along. No, you're counting the saddle point for this, and the fact that the saddle has a non-trivial R charge doesn't make any statement about the states.
Okay, does not.
Yeah. Okay. I mean, yeah. Okay. I mean, you can. That's true in try to estimate the growth of states of any growing function, and what you'll find always that there's some kind of complexification, and it looks like the saddle point is sitting at a place where the original integral was not defined. That's a very generic phenomenon. Okay, so now there is an issue here, namely that if you remember the history of this subject, from the gravitational point of view, often the starting point is you start with the extremal black hole solution, and then in order to do any calculations, you use the attractor mechanism. That was very important. What happened to this? Yeah. And that tells you that all the scalar fields get fixed, and you have an ADS 2 times S2, and that's always a starting point for any calculation. Here I don't have an extremal black hole, so I have to revisit this. And what we found in this paper, this is with Jan Boruch, Luca Iliescu, and Joaquin Turiachi, we found that there's actually, although there is no extremality, there is a new type of attractor mechanism that arises in these saddles. Then I will apply this to the heterotic string theory, and there are some interesting surprises. Okay, I'm going a little behind time, but that's fine. So any questions about the main part, the motivation and so on? Okay. So let me first start by illustrating this in the simplest context. This is just pure supergravity. Pure supergravity means that the bosonic action, so it's a 4-dimensional theory, it's just Einstein-Maxwell theory. Okay, and then there are fermions which make it into supergravity. Okay, but the solutions we're talking about are bosonic. Okay. So let me first just review the extremal rational Nordstrom black hole. That should be familiar to most people, and I'll use that as a starting point. So the starting point is you take a point charge. So there's one harmonic function which is 1 plus q over x. X is a three-dimensional vector in space. Okay, and r is the magnitude of that. So 1 plus q over x. And that harmonic function completely determines the field configuration. That's the metric, and that's the electric field. Okay, and you can practically read off from this. So the horizon is at r equal to 0. And if you zoom in at r equal to 0, you can essentially eyeball that there's an ADS2 times an S2. And you can see that the radius of the S2, sorry, the area of the S2 is 4 pi q square. Okay. Now, this solution admits killing spinors in the supergravity, and it obeys m equal to q. That's the supersymmetry solution condition. And now, here is an interesting fact that without supersymmetry, there is a bound on the charges in Lorentzian theory, on the Lorentzian solutions, coming from regularity of the Lorentzian solutions, which says that m square should be greater than or equal to q square plus j square. Okay. Now, on top of this, if you put m equal to q, then indeed you get j equal to 0. Okay, this is the statement I said, that four-dimensional asymptotically flat black holes do not supersymmetric, do not rotate. Okay. And then the Euclidean continuation of this gives you beta goes to infinity. Okay, that's the extremal black hole. Okay. Now I'm going to discuss my solutions. So actually the solutions goes back a long way. So the question is, first let's ask, what's the most general class of supersymmetric solution? This is again well known to people here. This question was first asked by Todd. And the solution is like this. It's determined by two harmonic functions, v and v tilde, okay, which I'll take to be like this. And the metric looks like this. It has this form. Now there's a rotation in the metric. And the rotational gauge field is determined by the two harmonic functions. Okay. And these two harmonic functions I can think of as two sources. So I'm going to take, so earlier I had one source at the origin. Now I've split it into what I call a north and a south pole. Okay. And these two determine the full configuration. That's the metric. There's also an electric field as before. But now notice that there's also a magnetic field. But at infinity, there's no 1 over r term. There's a minus sign here. So there's no new monopole charge. I'm not changing the charges, but there's a dipole field in the system. Okay. Sorry. Yeah. So there's that, and okay. So here this has become complex. So first I start by in the Lorentzian theory I have a minus sign with dt, and then omega is rotation. But now when I do that, first this also becomes complex for the usual reason. There's dt d phi. And then these things. But you can have these solutions without just Euclidean Sorry?
You can have Euclidean Isler-Wilson solutions, which don't have complex.
Yeah. So there's ways. So in fact, I'm going to exactly like in Ashok's talk. You can take the parameter, so the angular velocity parameter, to be imaginary, and the metric is completely real. In fact, that's the frame I'm going to do. But at the cost of making the angular momentum imaginary. Something or the other has to give. Okay. Yeah, so as you just said, these solutions were first discussed by Israel and Wilson and Perges. They also have, in the full supergravity, they have their m equal to q and they're supersymmetric. And now notice what has happened, that in the extremal case, you had a 1 over v square, and there was a double pole, and that's what gave you the ADS2, the extremal throat. And what you've done by sort of separating them is that close to, I'm using pole in two different ways, close to the north or south pole, this harmonic function has a single pole. And that means that it's non-extremal, because a single pole is integrable, so that means there's a cap. Okay. Now, the Lorentzian solution corresponding, if I just make this Lorentzian, that has a naked ring-like singularity. It's not a good Lorentzian solution, but the Euclidean solution is smooth and it's perfectly well defined. Okay. In fact, the way to think about this Euclidean continuation was given this nice paper of Hartley and Hawking. You think of this omega, this rotation gauge field, as a three-dimensional gauge field, and then these sources means that there are Dirac strings for these gauge fields coming out of the poles, and smoothness would mean that this Dirac string can't hang out, so it can start at the north pole and has to end at the south pole. Okay, and that condition then tells you that beta omega equals 2 pi I. So what it's saying is that these smooth solutions in this setup automatically fix you to the supersymmetric theory, a supersymmetric solution, and then it also fixes the distance between the two centers. So that was a parameter here, and that's fixed in terms of the charges and the temperature. Okay. Now, this solution, maybe not everybody has seen it in these coordinates, but I assure you everybody has seen it. After all, it's a black hole with mass, charge, and angular momentum in Einstein-Maxwell theory. It's the Kerr-Newman solution, written in some different coordinates, and there's a coordinate change, which will explicitly bring you to Kerr-Newman coordinates. Okay, I don't want to dwell on that. In either of these two coordinate systems, you can calculate various things. So there's an angular velocity, which now I've made Euclidean. So it's omega times beta is 2 pi. And now you see that the angular momentum has an imaginary sign, imaginary term. And now you can calculate the on-shell action of the solution in either of these two coordinates, and you find that firstly it obeys the Gibbons-Hawking relation. So what I mean is that, so this is the BPS mass, beta times the BPS mass, and then there's energy and angular momentum, and there's correspondingly the entropy and this Legendre transform term. Both these terms are not simple. There are some complicated functions of Q and the temperatures, but the sum it just gives you exactly the extremal entropy. Okay, there was some confusion about this in the previous talk, so this is what is going on. So each term, so on one hand, so this area now, you can measure the area in the Euclidean theory and formally associate an entropy, but that's not the good object. That's beta dependent. But the free energy, which is what you should be measuring because you have gone to the grand canonical ensemble, it gives you the extremal free energy. Okay, now next is sorry, bound on this A, you mean?
Yes.
Yeah, but now this has become complex, remember.
Okay, but the fact that this is for Kerr-Newman, A should be less than 1.
In the Lorentzian theory, there was a bound like that.
You can take here.
Okay, so now I'll lift this to supergravity. So n equal to supergravity. This has 8 supercharges. There's a graviton multiplet coupled to nv plus 1 vector multiplets. Each vector multiplet has a gauge field, a complex scalar which I'll call y, and some gaugini. And the solution carries charges, electric and magnetic charges under all these gauge fields. Often this is called x for the experts. I've called this y to distinguish, to signal that it's some rescale value of x which obeys these equations, in case you actually note down these equations and work with them. Okay. The two derivative action is completely determined by a function called the prepotential, which is a homogeneous degree 2 function in these scalars. And in type 2 string theory in Calabi-Yau, that prepotential is completely governed by the triple intersection numbers on the Calabi-Yau. You have the cubic prepotential. Now, here again, you can ask, what is the most general supersymmetric solution? And this was asked and answered in various papers. And again, you have this IWP type of metric, a rotating metric. Here I've shown you a Lorentzian metric, where again the rotation gauge field is determined by harmonic function. So now you have NV plus 1 charges. So now you have 2 times NV plus 1 harmonic functions. You can think of this as sources for electric and magnetic charges. And the blackening factor is determined by the scalar fields. And the scalar fields themselves are determined by the harmonic functions. Okay, these are the famous generalized stabilization equations of n equal to supergravity. And note that this is algebraic. Namely, so GI here is the first derivative of the prepotential. So this determines all the scalar fields in terms of the harmonic function. You can plug that back and get the metric. And then there is also electromagnetic fields, which are also determined by the harmonic functions. All right. Now, if you put all the harmonic functions again at one point, so this h now is a vector. This small h is what replaces 1 for the simplest case, and now that is interpreted as some modular fields of the supergravity. And this gamma is the charge vector. Then you get back the spherically symmetric attractor black hole. You can see as r goes to 0, then all the scalar fields go as 1 over r times a constant, and the equations now become just a sort of not without the adjective general, just the stabilization equations or the attractor equations for the scalars. This might be more familiar. okay, in terms of the charges. And now you can solve this, and I'll call the solution y star. There you go. And then this is the extremal metric, and you can again see that the entropy, you can read off the entropy in terms of these attractor values of the scalars, and a small calculation, it takes 5 minutes, will show you that you can rewrite this extremal entropy in terms of the prepotential and the scalars at the attractor value, at the horizon. In fact, this form of writing it, this is the Legendre transform of the imaginary part of the prepotential at the horizon, was famously used by Oguri and Strohm and Jarmafa. But you can check this using these formulas. And now the solution, the non-extremal solutions look like this. Again, you just split the sources into two, north and south pole, and you give charges, and you allow for sort of, so there's the monopole charges, Q and P, and you allow for other dipole charges, okay, what I call N and M. And so I won't go through the whole derivation. Let me just show you the equations and the parameters. So the data that we have from the boundary is the monopole charges, that's fixed, and there's one real parameter that is either the temperature or equivalently the angular velocity, that's fixed. And the parameters of the solution are the dipole charges, right? That's not fixed from infinity, it dies off much faster, and the size, the distance between the two centers, okay? Or as we saw, that is related to the angular momentum. And let's count equations. You have as many BPS equations as charges, so that's that. And then you have one smoothness condition as before, and that's a real condition which involves all the charges and the distance and the temperature. And so together you have the same number of equations as parameters, and you can solve this. Okay? Good. This is one of the things I wanted to talk to various people. Except for this right-hand side.
Yeah.
Okay, so let me postpone this question. So the answer is yes, definitely. I was hoping. Thank you. I was hoping somebody would notice. I want to discuss this. There are two differences. One is the beta, but also the eyes, which is not very clear, is different. Okay.
Also, it's only constraining south and north talking to each other. It's not constraining north with north. Is that? No. It's sort of like a hedgehog quiver. Yeah.
It's just a two-centered. So the Lorentzian analog of this is a two-centered black hole. So it's literally that. Okay. So keep that thought. We'll come back to it. And now you can calculate the free energy. Again, I'll just stay here. So let me just contrast the extremal and non-extremal black hole. So the extremal attractor has a spherical horizon, and the scalars are constant on the horizon, and they're determined by these attractor equations. Okay. The non-extremal solution I'm discussing is not spherically symmetric, it's rotating. And the scalars on the horizon are not constant. They depend on the angle, depend on where you are on the sphere, they depend on the temperature, and they depend on the asymptotic moduli. Okay, they're not the nice objects. Okay. And the area of this is also some complicated function of all these moduli and beta. But something nice happens. Namely, if you look at these generalized attractor equations near the north, so there's a pole because there's a rotation, so there's a distinguished north and south pole. Near the north pole, what you find is that the scalar fields y take their extremal values, extremal attractor values, but the conjugate y bar becomes 0. And here you see another very clear manifestation of the complex nature of the solutions. Y bar is not y star, not the complex conjugate. And at the south pole, the opposite happens. Y is 0, and y bar is the attractor value. And now you can calculate the action. The action takes essentially the same form like I presented for the extremal black hole, except that now, instead of the Legendre transform of G minus G bar on the horizon, that's not well defined anymore, it's the Legendre transform of G at the north pole minus the Legendre transform of G bar at the south pole, okay, with respect to y and y bar.
So what happened with the charges of the black hole? So because on the left hand side you have like P and Qs, and they disappeared. So
No, they're perfectly, the charges are definitely there. So here, so this solution carries the same monopole charges, and it also has dipole fields. So here when I said, so notice here, let me guide you through this. So let me start from here.
no,
Okay.
I meant like for the attractor equations, you have like P and Q, and so why don't you have like some gammas, right, instead of the?
So I'm not sure I understand. Let me just make some comments and ask the question
yeah,
again.
yeah.
The y at the North Pole, the statement is that y at the North Pole is equal to the extremal attractor value, which is determined by this equation, by solving this equation in terms of P and Q. That's what I called the star solution a few slides ago. So this one is determined only in terms of the charges, and so is this one. Now when you look here, it's the same thing. G, so you can plug that back. All these quantities are determined only by the charges, by the monopole charges.
Okay.
Is that clear?
Yeah. Thank you.
All right. Other questions? Okay, so I think I'm in time now, so I'll just now go to the two-charge ensemble, which I began my talk with. So I'm going to apply these ideas. So the two-charge system, you can embed, you can effectively write in this n equal to 2 supergravity. And you have to first say what is the prepotential. The prepotential is this. It's x1 over x0 times CAB times XA XP, where CAB is a bunch of numbers which you can, which are equal to the second double intersection numbers on K3. And that's not an accident, because you can calculate it, for example, using heterotic type 2 duality, in which case heterotic on T6 is type 2 on K3 times T2. And now the Calabi-Yau is like K3 times T2. And so you get x1 over x0 times double intersection number. That's the full triple intersection numbers. Now the charges are Q0 and P1. And now you can just, so I just showed you the attractor equation. It's very simple to solve for two charges. Can do this in 10 minutes with this prepotential. And that's the solution. Okay, that's the North Pole and Y and G. But now you see that this solution is actually singular. Okay, the idea when we started this paper, we had this idea that once you include rotation, it's going to desingularize everything, and it almost does, except at the poles. Okay, so you can see it's singular because in the heterotic frame, the y1 over y0 is the dilaton, and that blows up. Okay, and it blows up with this with a sign so that G string actually goes to 0. So what this is saying, there was some question about this in the previous talk. What they're saying is that the Einstein frame metric is perfectly smooth, and it's even weakly coupled, but the string frame is highly singular because G string goes to 0. You have to divide by it to go to string frame. So when you talk about alpha prime corrections, you're in trouble, meaning it's a very singular solution. And the same conclusions can be reached by analyzing the heterotic supergravity. We heard a talk about this earlier today. But the advantage of this n equal to 2 supergravity formalism is that one can include a class of higher derivative terms. And this is done by first calculating what's called the Weyl square. So that's the gravitational Weyl square tensor. You think of that as a scalar field, and there's a way to supersymmetrize that, which is given by this formalism. So I'm using this formalism of conformal supergravity. Okay, I hope I gave a reference to that earlier. And it looks like this. So that's the prepotential, that's the cubic prepotential for a generic Calabi-Yau. And then this is the first correction terms. You have another term here, upsilon. There's a number C, which is actually 1. I'll come to that. And then there's like higher and higher powers of upsilon. Okay. In the Calabi-Yau interpretation, these terms correspond to the higher and higher genera of the topological string on that Calabi-Yau. Okay. Now this is a much harder problem when you include the this is the 4 derivative term. This is Weyl square, which has 4 derivatives, because because it's a 4-dimensional gravitational term, and now we don't have ADS2 symmetry, okay, because it's a non-extremal solution. The full equations are analyzed in all the glory in this paper. But what we found was something nice, that near the poles, these equations simplify. Okay, so at two derivative levels, the equations have a nice form. There's the metric which I showed you, the IWV form, and there's the generalized stabilization. All of that has to be revisited for a general prepotential, and that's been analyzed here, and it's highly differential. It's not algebraic at all. But near the poles, you again get algebraic equations, and you can solve that, and what you find with this prepotential, and this is your answer. Y and G take these values here. So C is really 1 in the example that I'm discussing, but I've just put a C there to show you that if you artificially didn't take if you only took the two derivative term, this would be 0. So just to say that that's the thing that's making the thing non-singular. So this is a paper with Yiming Chen and Joaquin Turiachi. And that, good. So now the next task is to calculate the action. Another question.
You say that you can find, so in the previous slide you can find the values of y's and g at the poles, but then not if you're not in the poles, then the equations are transcendental or whatever, so you cannot solve them. But do you know if, like, numerically at least they are close to the values that you're mentioning here? I mean,
yeah, we also tried to study it numerically. Oh, yeah, so there's a lot still in progress. We didn't get very far with numerics. If you're good at it, I would love to talk to you about this. I'll tell you what the problem is later, but maybe that's a problem that can be solved. Yeah.
So what's the rationale for only incorporating these particular higher derivative
Wonderful.
terms?
Just bear with me for one more slide. That's an important point. In fact, I should have... let me make comments on that. Okay. Now we want to calculate the free energy. Now, that's a difficult problem. We haven't solved it. We have some ideas. And what we did in the paper is to say that the action takes the same form as in the two derivative Lagrangian, so there's various ways to write the action in the two derivative Lagrangian, and I chose a way which doesn't depend on the details of the prepotential. Yeah? And that's the guess that we're making for the full theory. That is the Legendre transform of the prepotential at the North Pole minus the conjugate prepotential at the South Pole. And with that form of the action, you can show that the free energy, which is the log of the index to leading order, is exactly 4 pi square root of n double.
Can you just remind us, in the case of the single-centered, where you also wrote the free energy as some Legendre transform the imaginary part of G, like that holds also in the higher derivative theory, right?
Yes. So when you have ADS2 symmetry, it's fairly easy to show that.
Right.
That's right. Here it's...
here you're assuming
that
this
we're working on it. So we think this is the case.
Okay.
Yeah.
Thank you.
Another question? Whichever. Ashok first.
Yeah. So if you take the action that you have written, it admits an ADS2 times S2 solution.
Yes.
Right?
Yes.
And doesn't that lead to all the problems that you mentioned at the beginning? That I mean, you may not be using the ADS2 times S2, but the fact that ADS2 times S2 exists as a solution, that will be incompatible with supersymmetry, right?
Yeah. So this is the same point you made at the very beginning, more or less.
Yeah.
Okay. Maybe I want to discuss this also. I'm almost finished, and then I want to discuss that. Yeah. Did you have something to say, or was the question?
No. I'm just asking. So
the
same contradiction will apply to this.
Yeah. Exactly. Yeah. Sorry, here's another question. If you wait for 2 minutes, I'm going to finish, and then Okay. So now let me answer Emil's question. So is that another miracle? How do we explain this? Now notice that, as was correctly pointed out, and let's go here. Sorry, I wanted to go here. Here in general, there's an infinite expansion. So there's both physics, there's nice physics and nice mathematics. So what is the physics? The physics is that if you have a solution which is singular if I only have two derivatives, and it's non-singular at 4 derivative level, that means that you're playing off 2 derivatives against 4 derivatives. That means that you must also include 6 and 8 and everything else. Okay, that was the comment. So what might explain this kind of miracle?
There are various other higher derivative terms in the action.
Yeah, okay, so there's that, and this is only the F-type term.
Yeah,
okay,
yeah.
right. So okay, good. So I have an answer to one question and not to the other. Notice that if you think of the type 2, if you think of this in the type 2 language, then the Calabi-Yau K3 times T2. Generally speaking, a Calabi-Yau is an infinite expansion of F terms, and that's just exactly the topological string. But on K3 times T2, because the T2 has fermion zero modes, the topological string expansion terminates at one loop. It's exact at one loop. For T6, it's exact at tree level, K3 times T2 at one loop. So for this particular example that I'm talking about, this is the exact prepotential. There are no dots. Okay, so that's half the answer. But then there's the other half, which is what about the D-type terms? So there's just one class of supersymmetric terms. Roughly speaking, in n equal to 2 supergravity, you can divide supersymmetric terms in the Lagrangian in two types. I'm calling it F and D based on n equal to 1 supersymmetry, but it's essentially the same thing. There's a superspace formalism, and the F terms are holomorphic half superspace integrals of holomorphic functions, and the D terms are full superspace integrals. Yeah. So D terms, this is suggesting that D terms don't contribute. And there is some precursor to such statements. So in ADS2, so Val and I worked out that in ADS2 and also certain off-shell geometries of ADS2, exactly that happens. So we're hoping that there is some statement of that type here. Okay, so that brings me to the end. Let me just recap. So the gravitational index is captured at the saddle point level by these non-extremal supersymmetric Euclidean black hole solutions. And I didn't show you, but for sort of big black holes, this works without any problems, without all these caveats. And you can calculate. This was the first paper with Jan and Luca and Joaquin, where we checked that indeed this works, and the gravitational index equals the microscopic index, at least at leading order. So unlike the string black hole transition, where there are these two different pictures and you try to match them, here it seems like there's some kind of a duality, that the two pictures are just dual languages describing the same physics, and there's just an equality of the index as there should be. The techniques, as was noticed, could be used for, instead of two poles, you can have many poles. You can ask what are those solutions. And physics-wise, you know that this was sort of the non-extremal version of one black hole. But you can also have two, these supergravities also admit two black hole bound states and multi-black hole bound states. What are the non-extremal analogs of those? So that's work in progress with Jan and Luca and Joaquin. And there's a whole notion of wall crossing. And that's where I believe that this formalism will really come into its power, because now you're, unlike in the old days, now you're putting all of that into one path integral, and you can just analyze this path integral. You can also ask what about higher dimensions. That's also work in progress with these people plus Roberto. There's some big goal of deriving, maybe you can localize the supergravity starting from asymptotic flat space, including all these saddles. And this is what I want to end with, that technically, so up to factors of I, and the presence of beta, these solutions look, the equations and the solutions look, well, the equations, as was noticed, look exactly like the various bubbling solutions. Sorry, the equations look like the whatever the equations are called, and the solutions look exactly like the bubbling solutions. Okay, the physics, of course, is different. Here we're discussing saddle points, not individual microstates. So thank you very much for your attention. Questions? Okay, we can discuss this now, yeah.
Yeah, so I'm just coming back to this question again. So the argument that you gave at the beginning, right, seems to say that any action that admits ADS2 times S2 as a near horizon solution for this small black hole should be inconsistent.
No, I don't think so.
Yeah.
That's not what I said. So let me think what I think the picture is here. So let's first discuss big black holes, where clearly there's an ADS2 solution.
Big black holes, there are no problem. Yeah.
Okay, so let's see why there's no problem. So for big black holes, you have non-extremal solutions, and there's a beta parameter, and you can ask what happens as beta goes to infinity, and there is a smooth sort of, you connect smoothly with the ADS2, okay, as beta goes to infinity. But there's also another solution when there is no beta at all, and there's just an ADS2 times S2, okay. Now, it's that last thing that I will question for the two charged black holes. So there's a limit here, okay? But what I think is happening is that limit is not the same as just the ADS2 times S2 solution of the two charged black hole that you're discussing. Because you can't just go from omega equal to 0 to omega equal to 2 pi freely, unlike in the big black hole.
Yeah, but nevertheless, that solution exists, right?
Yes, yeah.
And once the solution exists, doesn't that lead to a contradiction? Because once the solution exists, then there is a conflict to the supergroup, right?
So content to?
With the supergroup, that you don't have that.
Yeah, so that may not be stable, right? So if you look at the supergroup and you ask, is there a Schwarzian theory whose broken symmetries correspond to that supergroup? Okay, so we analyzed that in the paper. And then, well, the answer is no. So that also means that there's sort of no nearly ADS2 geometry. It could be that that solution is just not stable from this quantum mechanical point of view. That there is a solution, but okay, I don't know.
Yeah, okay,
I'm sure it has some meaning, but it's not the usual meanings that we give to it.
Okay.
Any other question, comment? Okay, so then let's thank Samir once again.
Thank you.